Hello and welcome back. In this video we'll continue looking at section 5.2 on the binomial distribution, and we saw this formula for the probability of getting x successes out of n trials. So let's briefly review that. So we're going to repeat a trial n times. So this is, n is the number of trials, and so in this formula, x is going to represent the number of successes, whatever we deem to be a success versus a failure. P is then the probability of success in any one trial, and Q is the opposite, is the complement. This will be the probability of failure. And I started to look at breaking this down last time, so I quickly want to just mention this again. This number has three parts. The first part, the second part, and the third part. The first part, this is a formula that you will have seen before. This is n choose r, as in the number of ways to arrange all of our successes and failures. So if we have x successes, we'll have the rest of them, the n minus x remaining trials, will be failures, to arrange x successes and n minus x failures. So this is just counting how many different ways can we arrange our successes. Do we go success, failure, failure, success, success, or do we go failure, failure, success, success, success? This is just counting how many ways to do that. P raised to the x power. P is the probability of success. X is the number of successes. So this corresponds to having x. So this is the probability of x successes. Whereas this one, Q is the number. Q is a probability of getting a failure, and n minus x is the number of failures. So this kind of corresponds to the successes that we see, and this corresponds to the failures. So each part has a purpose. This is counting how many ways there are to arrange them. This is the probability of just the successes, and this is the probability of just the failures. So let's apply that to this next problem. If the probability of making a free throw is 0.9, what is the probability of missing one or fewer free throws out of 10? Okay, so we'll use our formula, and we'll calculate the probability of making one or fewer free throws. Now, to begin with, what I want to do is I want to point out that we're going to miss one or fewer free throws, which means that we are going to make, so this could be phrased as making 9 or 10 free throws. If we're going to miss 1 or 0, it means we're going to make 9 or 10. So what we want is a probability of making 9 free throws or making 10 free throws. And when we see an or, we want to think addition. So 9 and 10 are mutually exclusive. They can't overlap. I can't make exactly 9 free throws and exactly 10 free throws at the same time. So this is just going to be the probability of making 9 free throws plus the probability of making 10 free throws. So let's find both of these. So first of all, the probability of making 9 free throws. We have our formula. This will be the number of free throws we're shooting divided by the number of free throws we miss, factorial, times the number of free throws we made, factorial. And that's the first number. The second number here will be the probability of success raised to how many successes we want. The probability of making a free throw is 0.9, and we want to make 9 free throws. And the probability of failure will be 0.1. If the probability of making a free throw is 90%, the probability of missing a free throw will be 10%, and we want to miss exactly 1 free throw. So if you go through this and calculate this, I did this beforehand, you'll get about 0.387. There's a lot more decimal places back here, but I've just rounded to this for now. The probability of making exactly 10 free throws. There are in fact two ways of doing this. I'll use my formula first, and then I'll point out something that happens. So we're shooting 10 free throws. We have 0 misses and 10 makes. The probability of making a free throw to the 10th power, because we're going to make 10 free throws, times the probability of a failure raised to the 0th power, because we're going to miss 0 free throws. And if we calculate all of this, we will get 0.349. And so then I can plug this back up into here, and we can get 0.387 plus 0.349 is going to be 0.736. So this is the probability of making either 9 or 10 free throws. Now, down here, there's a couple of things that simplify. One is 0 factorial. We should remember 0 factorial is always equal to 1. So if we divide something by 1, it doesn't really matter. So then we have 10 factorial divided by 10 factorial. This whole first term is just 1. And also anything to the 0 power is also equal to 1. So this term right here is also equal to 1. So the only thing that matters is we've just got 0.9 to the 10th power. And this makes sense because if we want to see the probability of making 10 free throws in a row, the first free throw will be made at a 0.9 probability. The second free throw will be made at 0.9 probability. The third free throw at 0.9, all the way out to the last one. And with the multiplication rule of probability, since we're doing each one of these consecutively, we just multiply them all together, and we get 0.9 to the 10th power. This formula makes sense for making 10 free throws in a row. This top formula is a little bit messier, and with the odd numbers popping out, it's a little bit harder to see. This one makes more sense, but ultimately, we have the formula, and you might as well plug it in and use it. I will show how to use StatCrunch to come up with these numbers without having to use a formula as well in the final video. So a couple of other interesting things. We can talk about parameters of a binomial distribution. So the first one, the mean, is just going to be the number of trials that we do times the number of successes. And we'll see that this makes sense in a second. We have a formula for the variance and the standard deviation. The standard deviation, maybe a little bit more important than the variance, is the square root of n times p times q. So let's come up with these guys in an actual problem. So let's look at a problem that'll make sense. We'll flip a coin, and we'll flip a coin 100 times. The probability of flipping heads is going to be 0.5. So then we could ask, what's the expected number of heads? And we might expect, if we're flipping a coin, about half of them should turn up heads and half of them should turn up tails. So we might expect to get 50 heads in 100 flips. Let's see if our formula agrees. The expected value of a distribution is equal to its mean, and the mean is just going to be n times p. So n is the number of times we're number of trials, so this is just going to be 100, and the probability is the probability of success, and if we call getting a heads success, well, that's going to be 0.5, and lo and behold, we get 50. So the expected number of heads is 50. So it matches exactly what we would expect. The standard deviation, so the standard deviation sigma is going to be the square root of n times p times q. So n is the number of times number of trials we're doing. So again, we're flipping a coin 100 times. P is the probability of success, meaning the probability of flipping a heads. Should be 0.5. Q is a probability of failure. Flipping a coin, the failure would be getting tails, and getting a tails would also happen with probability 0.5. And then we want to take the square root of this. So let's simplify this. 100 times 0.5, so that's a half of 100. So that's 50 times 0.5. But half of 50 is 25. And the square root of 25 is 5. So 5 heads is the standard deviation. So remember that the standard deviation is roughly corresponds to the spread of the data. How spread apart is the data? And this last question asks, is flipping 63 heads unusual? And there are different ways to tell if something is unusual. One of the ways we mentioned right here uses our rule of thumb, which is anything more than 2 standard deviations away from the mean is going to be significant, meaning it should be unusual. So down here, if our mean is 50 and our standard deviation is 5, this means that values bigger than bigger than 50 plus 2 standard deviations, which is going to be 60, are significant. So 63 heads, getting 63 heads would be a significant event, and we would consider that unusual. Likewise, we could go the opposite way. Let me draw a line to separate this out. I'm running out of space here. Values smaller than 50 minus 2 standard deviations. So if we go 2 standard deviations below the mean, these would be significant, as in significantly low. So this is just using our rule of thumb, which corresponds to how many standard deviations away we are from the mean. The other way, which will come up a little bit in the homework, is we look at probabilities of something happening. Let me use a different color. So anytime that the probability of an event happening is going to be less than 5%, less than 0.05, then we consider that unusual. So if the probability that we get X or more successes is less than 5%, that is a significantly high value, as in this event, if this were to occur, would be unusual. If the probability of getting X or fewer successes was less than 5%, then X itself would then be significantly low. So there are 2 ways of determining significance. Either you look at it in terms of standard deviations, or you look at it in terms of probabilities being less than 5%.